In this second video, looking at the WaveShare OpenEPM1270, I thought we'd look at the supplied schematic that I downloaded from the WaveShare website and kind of go through the sections of the schematic. So across the top of the schematic here, there are 3 blocks that all are defining pins on the CPLD device itself. So the CPLD device has got a load of pins around the 4 edges. And this is just simply saying that pin 1 is IO1, etc. So there's a group of pins here, a group of pins here, and a group of pins here. For the guy who drew the schematic, it was just easier to have these smaller manageable blocks than one giant block. There's a 4th block of IO pins as well on the device defined here. So you can see you've got tons of IO. We then get into the control pins for the device, which is what this block here has on it. So the device itself requires a lot of ground pins, which are defined here, and a lot of VCC pins to bring the 3.3 volts in. So a number of pins are dedicated to the power. On the back of the board, you'll see some decoupling capacitors that provide decoupling here. There's 4 potential clock inputs on it. Fitted to the board is a 50 megahertz oscillator, which is represented here, which is driving pin 18, this G clock 0 pin. There's a footprint on the board for a second oscillator that's not fitted that goes to pin 20. There's a set of pins over here, these top 4, the TMS, TDO, TDI, and T clock. Those are for the JTAG interface, which is how you program the device. And they're connected over here. And if you remember from the previous video, there's a 10-pin header on there that the ribbon cable goes from the USB blaster to the board. This is where those control signals come to the board to download your design to it. There's a reset where you can reset the device. There's a little click switch on the board itself, and then it goes to pin 61 on the device, which is the device clear. So getting through these, this just has to do with defining the I/O pins in the schematic. In this case, these I/O pin numbers you'll see show up in other places down lower in the schematic. It just gets the device defined, the basic control logic for the device, clock, reset, power input and output. We then in the schematic come around to decoupling capacitors. So there's a number of these 0.1 microfarad decoupling caps. The majority are on the back side of the board underneath the device itself. Around the edges of the board there's this, it's labeled 8 IOs _ 1. This is basically that little 10-pin connector. It's got 3.3 volts in ground and then IO 1 to 8. And if we come back up at the top of the schematic over here, we'll see that IO 1 through 8 are defined as these pins on the device. And we will come around to a second picture I've drawn to make this easier to see. We have a second block of 8-bit I/O. Again, it's got 8 IOs, power and ground. We have a block that has 16 IOs, and it's got power and ground on 2 pins, and then 16 IOs defined. And finally, the block with 32 IOs, which is actually drawn right here. So this is the connector on the edge of the board that's labeled 32 IOs. It's again got power and ground, and it's got this whole series of IOs defined here that are brought out to it. And I'm assuming these labels in here are defining other stuff. At this point, I haven't looked to really understand what these are. I can guess from a couple of them. I think the 50 megahertz clock may be brought out here, or maybe you can divide that clock. And looking at PB and PD, I'm guessing there might be like the internal concept of ports in the device, though I don't know that. The next thing you'll see in the schematic here are these 4 blocks. And if you remember in the center of the board, in the board picture, there are 4 yellow pin headers, and that's what these represent. Is you've got those pin headers that you could use to jumper off to other boards. There's a 3-wire interface that temperature sensor chip can go into. It is a serial device. You've got ground and power for that 3-pin device, and then a data line where you can read the temperature out of it. There's 4 LEDs on the board. There's a jumper block here where you can enable or disable the LEDs. It might be that in a project you wouldn't want these LEDs hooked up because you're picking these IOs up. Perhaps, oops, scroll too far, off one of these connectors over here, those yellow ones in the center of the board. Thing to note here is the LEDs are tied to 3.3 volts. So you're going to take these IO pins low to light the LED. You've got, you know, plus 3.3 on this side, and by making the IO pin low or ground, the LED will light up. So there's this buzzer on it. There's a jumper to enable or disable the buzzer, and basically you would be driving some kind of a square wave to this transistor to make the buzzer make noise. Let's see if there's anything else along this edge that I've missed. And we'll keep looping around. There's a connector on the left-hand side of the board that is a 16-pin single inline connector, and this is used for plugging a kind of a standard LCD interface down into. You can put kind of a 2-line, you know, 40 character, whatever you want. You know, LCD display can be plugged down in there. It's got power pins to pick up power for the device and for the backlight. And I believe this resistor here is used to set contrast. It's fixed, and it's driven from these set of IO pins. If you've dealt with LCDs like this, there's typically a parallel interface, and you're sending information to it and then clocking it in. Let's continue to scroll through here. There's the power input to the device. This is the little cable that plugs into a USB port but only brings in the +5 and ground. Power switch. This is effectively regulated down to 3.3 volts. There's, I believe, a poly fuse here, so if you drew too much current, this would keep you from damaging things, and of course a power LED. And then this VCC33 here is the 3.3 volt feed that goes off to all the other places in the schematic. There's a little joystick port on the device. It's got a little push button joystick. We looked at that kind of in the first video. You know, up, down, right, left, and push all pins. It's got 4 pins on it that are the outputs. It's got a C and D pin. So what I can do is take D low. I believe I'm interpreting this correctly. Let me step back. I'm misinterpreting this. Let me step back. So there's the A, B, C, and D that are the up, down, right, left, and then there's a center pin which says you push straight down on it. There's a common to all 5 of these that is grounded, and what you're doing on the device is you've got an active pull-up resistor. So these pins are being pulled up by the device to 3.3 volts, and if you push up, the appropriate pin for up would get grounded because you're closing a switch to ground that, and that's how you would read the joystick. You would see all ones unless one of the switches was closed because you were using the joystick. And again, you can see the IO pin numbers assigned to that. We looked at this a second ago. It's the 32-pin header. There's the other 2 headers off the center of the board, and that's pretty much it. So this schematic can be rather confusing. I don't think it makes really clear what's going on here. So as you saw in the first video, I've gone ahead and drawn up this picture. I've grabbed a picture of the board itself, and I've taken bits and pieces of that schematic, and I've captured those, and I've indicated here kind of how things are wired. So we have that 50 megahertz clock we talked about that goes to IO pin 18 on the device. We have the unfitted oscillator where you could have a second oscillator. We have that first 8-bit IO port on this connector here, and here's the pin out for it. If you look over here, you'll see that that pin has a little square around it and the others are open. That tells you that's pin 1. So pin 1 here would be VCC, ground, and then IO 8 through 1. We have a 32-pin IO. We looked at this a minute ago as well in the schematic. Again, pin 1 is in this corner here. So pin 1 has got VCC. Pin 2 has a VCC, and then or pin 1's VCC, 2's VCC, 3 is ground, 4 is ground, and then the IOs is defined here, come across the device. We have the 16-bit IO. Same thing, I believe pin 1 is this corner up here, and it is. And again, you get the pin out and you know the IO pins. And just to say it again, IO 93 here refers to pin 93 on this device. You can probably also pick up IO 93 right here. So that pin 93 on the device is available right there on that pin, and also on one of the pins on this IO block. And that's true for all of these pins. They're typically brought out to these connectors. You could use jumper leads off to your own board or plug in here. There's the second 8-bit IO, 8-bit IO number 2, and it's the same thing. Pin 1 is VCC, pin 2 is ground, and then IO 51 to 42. There's a reset switch here. We saw that reset in the schematic. This reset takes pin 61 on the device low to tell it to reset. There's the joystick we just looked at, where if I'm pushing on the joystick in some direction or straight down, one or more of these output pins will be pulled low. These are going to IO pins, or device pins 38, 39, 40, 41, and 37. So you can tell here again, these refer to the pins on the device. And you'll also find like there's IO pin 41, 43, 39 right here. So you could also pick up the signals from this joystick here on these pins to bring off to another device. Or however you want to do this. Normally the joystick switches are open, so you could use these as general IO if you wanted to. There's the 3-pin device where that little 1-wire temp sensor goes in. It's got ground 3.3 volts, and it goes to IO 12, which is also up here on a pin. You've got the 4 LEDs here on the board. You've got a set of jumpers to enable or disable those LEDs. If you wanted to use those IO pins for something else, you could pull those jumpers out, and that way you wouldn't be lighting the LEDs and taking the current load, etc. from it. As I mentioned before, and I'll say it again, these LEDs are through a current limiting resistor to VCC. So you're going to take IO pin 14 low to turn this LED on. IO pin 15 low to turn this pin on. There's the LCD connector that we described earlier. Again, back to ultimately pins on the device. So I personally find a drawing like this easier to look at. Once I get my text blog up on the device, I'll make this picture generally available. It's not up there now. I'm still refining it as I discover things that I've got incorrect. But I think at this point this is pretty accurate. It gives you a way of taking what's drawn in the schematic and taking it to the physical connectors on the device or the physical switches, etc. We talked a little bit about that power supply where the 5 volts comes in off the USB connector. You've got that on-off switch we saw in the schematic. You've got the 3.3 volt regulator. You've got that poly switch sitting down here. So if you manage to short the 3.3 volt rail here, that poly switch will keep you from destroying the regulator. Of course, a power LED to tell you the board's on or off. This is going to be an input filter capacitor for the voltage regulator. I think there's a couple more capacitors sitting here. There's a jumper here for the buzzer. In the picture it's off. If you've got the jumper over the 2 pins, which would be this jumper here, then you can actually drive the buzzer with it open. Buzzer doesn't make any noise. The buzzer is rather annoying. Personally, one of the demos, it just runs constantly and it's annoying, so I have moved that jumper off as is shown in their picture here as well. The reset pin's got a resistor and capacitor that produces a little RC time constant. When you close the switch, the capacitor is discharged, and then the capacitor through this resistor here takes a little bit of time to charge up, and that produces a low to high transition that resets the device. You've got the JTAG interface we talked about on the main schematic where your USB blaster comes in and connects. And it's got 4 pins that come back to the device that take control of the device and do the programming of it. So I think we've kind of walked around the entire board here, kind of looked at my interpretation of the schematic, and how various blocks are connected to it and various important signals. Next, I want to jump into, I think, the joystick demo, and we'll take that a little further apart and understand how it works on the board. So I'm in the pin planner, which in the programming environment is how you define what pins are going to do what on the system. I've just grabbed a quick capture of the part of the schematic here that had the LEDs and the joystick on it, and I want to look at the pins here that are defined versus the board here. So we have key down on pin 39. We have IO 39 defined here, pin 39. So we know C is the key down. We have key left on pin 41, which is IO 41, same thing, pin 41, IO 41, they're the same thing. So we've got the 5 switches for the joystick defined in the pin planner here, and we've told it the appropriate pins they're hooked to, and you'll see that this set of 5 pins matches this set of 5 pins. What this mapping allows us to do when we're writing our Verilog code is to use the string key underscore down to know that we're looking at the key down on the joystick rather than have to hard code in there pin 39. It would be really confusing in the Verilog code to see pin 39, whereas you can see key down and actually read it. We have the 4 LEDs defined here. There's a little array of LEDs here, LED 0, 1, 2, and 3 for the 4 LEDs. In this case, we know they're outputs, whereas in the joystick, we knew they were inputs. These are outputs because we need to take the appropriate pin low over here to light the LED. The pins are again defined 14, 15, 16, and 21, just as you see here, 14, 15, 16, and 21. For all these pins, we've told it it's going to be 3.3 volt level TTL signals. So, 3.3 volts is a 1, 0 volts is a ground, or 0. We've also told the pin it's got 16 milliamps of current strength. I am making an assumption here, and I could be wrong, but my assumption is this means this pin can source or sink 16 milliamps. So in the case of the LEDs, if I take IO14 low to light this LED, I could have up to 16 milliamps of current flow through the LED to light it. Obviously this LED uses much less current than that, and that current is limited by this resistor. And I guess we could do the math, 3.3 volts, 2K, you could figure out the current through the LED. I'm assuming these can be changed to be other ranges potentially. We've also got that reset pin, which goes to that device reset on pin 61. And back in the schematic and the drawing I did, if you remember, and let me bring it up here and we'll scroll over to it. Hopefully I can find it here. Right here. In this schematic here, we had this 50 megahertz clock that went to device pin 18. We've also defined a clock signal to pin 18. So our little program here that we're going to write knows that pin 18 has an incoming clock. We've got the reset here to pin 61 that's also been defined to the system, but on pin 61 you'll find a reset. So this pin planner is used to define what pins are input and output on the device and to give them friendly names that we can use inside of the Verilog code. So I've taken a bit of time to walk through the little joystick example of the Verilog code and add some comments to help me understand it, and I thought I'd talk you through those comments. So we have our Verilog module here. This module is going to do work for us. In this module we are defining these pins. We have the clock input. If you remember from the pin planner, clock was the pin 18, 50 megahertz clock input. We have the reset input, and that was on pin 61. The little reset button went to there. We have the key up, down, left, right, and Z. Those are from the joystick. Again, those are on, I don't remember the pin numbers. We'll look here in a second. And we have the LED outputs, and the LED outputs actually controls all 4 LEDs. So if you look at the definitions here, clock and reset are inputs for the clock and reset. For the joystick, we have 5 inputs, up, down, left, right, and Z. And then we have this little array here we've created. So with 4 bits, so bits 3, 2, 1, and 0. There's 4 bits defined there for the LEDs. The way this is going to work is any bits that are 0 in this little array of 4 will enable the LED that corresponds to it. In the pin planner, when we looked at it, let me actually pop back in and take another quick look at it. The pin planner. This is all. Oops, got it way too large here. Sorry about that. Let me get it back on the screen where we can see it. In the pin planner, we've got our sea of pins down here as we talked to just a minute ago. And of course, these pins up here are defined as these names here and associated with the physical pins on the device. So as I mentioned earlier, the pin planner allows us to use the term key down right here, rather than saying, rather than having to say, in this case, pin 39. So it just makes the code easier to read. So if we go to our little capture piece of the schematic I did, we've got the joystick sitting here, the physical joystick, and it's tied to these I/O pins. And again, those I/O pins are defined in the pin planner. And in this case, I/O 39 is the up, I/O 41 is the left, etc. And what this is basically saying is this. So this if statement says if this condition is true, then make this assignment. So it's going to look at the reset pin, which was defined back around to be pin 61, retrieve the value from it. Normally that pin is pulled high and it's 1. So if not reset, which means if not 1 is 0, which is false, then it won't do this. It'll say if this is true when it's not, because we've taken the 1 that is the value of the reset pin and we've knotted it to 0. So this condition is not true, so it doesn't do this assignment. Else, if key Z is pressed, so again, go out and read key Z. If I've got the little button pushed down, that input pin is not going to be a 0. If we take the knot of 0, 1, that becomes a true. Load the register with all zeros, which will turn all the LEDs on. Check key up, check key down, key check, key left, key right, etc. And as you fall out the bottom here, what you end up doing here is saying, take this little array we created here called LED and assign it the value of the LED register. So actually, this has the effect of writing whatever bit pattern we've loaded up here into this little array, which then sets the pattern onto the actual pins on the device. So if we look again at, let's jump back to the pin planner. I know I'm not explaining this super well. If we look at LED here, it's got 4 entries. It's a little array, 0 through 3, of device pins. And so by saying write to this little array, right here, right to this little array, it's going to write that value to these 4 pins, and this LED reg, it is a 4-byte or a 4-bit register. So take the 4 bits in that register, and in the end, I do that every time. See if I can get it to pop up here. Write that value to these 4 pins. So it looks at the various inputs, sets the appropriate bit pattern, and assigns it to those output pins. I spent a fair amount of time looking at this line here, these lines, and not really understanding this. Again, I am just scratching the surface on Verilog. Apparently this is what's called this little symbol right here, which looks like a less than, is actually a non-blocking assignment statement. And I really can't explain non-blocking versus blocking. I get it at a high level. It has to do with essentially race conditions. I do a lot of software development. I'm used to reading this as a sequential series of statements. If this is true, do this. Else, if this is true, do this. Else, if this is true. And you think of this as evaluating each one of these in sequence. The reality is this is being implemented in hardware. And you can get into race conditions. These things are basically happening at the same time, I guess is a way of saying it in the hardware design, how this gets evaluated and in the implementation in the CPLD. And blocking and non-blocking control kind of when things happen. I encourage you strongly to do some reading and explore blocking and non-blocking in Verilog. It's not something I've really got my brain wrapped around, and I don't think in this case it's required. I commented these two lines out, and the code worked just the same with those lines commented out or with them back in place. At first I actually thought perhaps this was a typo or something, but after reading up on this non-blocking operator, I realized that no, this is actually important. When you get to where you have multiple modules, and those modules are all, of course, implemented and running at the same time, and there are pins being shared between them, or variables, or whatever, being shared between them, blocking and non-blocking become really important. But hopefully this little description through this with some comments on it helps to find a little clearer what this code is doing. It's not really complex. I guess the other thing I didn't mention here that I need to mention is this always block. Always basically says I'm just going to always be doing this, and I'm going to kick off an execution of this on the positive edge of the incoming clock. And remember, in the pin designer, the incoming clock is pin 18, and that's the pin that goes to that 50 megahertz signal. So anytime that pin goes high, or the reset pin, pin 61, goes low, so we've got positive edge where the signal transitions from a 0 to a 1, or on the negative edge where it transitions from a 1 to a 0. Anytime those conditions happen, this block gets evaluated. So this just chugs away there. Normal execution, every positive edge of the clock, this happens. If you push the reset button, that will force a reset, and on the negative edge it'll also happen. And if it's reset, of course, it'll turn all the LEDs off. So hopefully this explanation helped a little bit. It's helped me kind of work through this and understand a bit more about Verilog. I've ordered a book. It'll get here in the next few days. I'll be reading. I've spent some more time kind of updating my notes and documentation. Anyhow, I hope you find this useful. If you do, let me know, and I'll kind of get some more of these videos together as I explore Verilog. And we'll talk soon. Bye.